Welcome back, everybody. This is our first session in JEE Mains previous year questions for chapter Atoms of class 12th. So, with this, we will go ahead and regarding previous chapters, there are a lot of videos available on our channel's playlist section, and you can watch them, find them useful, then you can share them to your friends, subscribe to our channel, and if you want to support us financially, you can scan the QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. With this, let's start today's video. Here we have the first one, the graph which depicts the results of Rutherford gold foil experiments with alpha particle is where theta is the scattering angle and y is the number of scattering particles detected. Now, first of all, let me draw a basic diagram that what is the scattering angle actually in this kind of scenarios. So, suppose this is our atom. This is our atom. And now we will going to have a path of alpha particle. So, path of alpha particle will be something like this. Yeah, let's use this color. It will be something like this. Initially, this alpha particle was moving in the straight line. Initially, it was moving in a straight line like this. And then what happens? That it start encountering repulsion from this nucleus. And due to that repulsion, it start deviating from its original path. And then it's deviate to a certain angle. Now, that angle will be measured. Yeah. So that angle will be measured from here. And this is the angle theta which we are discussing. This is the angle of deviation. Now, if you remember that in case of Rutherford scattering experiment, what happened that most of the alpha particles went straight. There was only very small deflection. So we can say that number of particles that is represented by y, it will be high for most of the particle for which deflection is very less, means theta is very small. So when y is very high, theta will be very small. Now, if we see here in the graph A or in the option A that y is high, but theta is not small. Here we are approximately pi by 2. So option A is rejected. Similarly, option B and C. Oh, sorry, not C. So in here, y is high and theta is less. And here also option D, y is high and theta is less. Now, we also know that these type of experiment obeys or shows exponent behavior. They does not show a straight line behavior. Their behavior is exponential. So from that, option C is also rejected. Only option D is left with us. So option D is the right answer here. Moving to the next one. In the Rutherford experiment, alpha particles are scattered from the nucleus as shown out of the four path, which is not possible. So it is mentioned that alpha particle is scattered. So we know that nucleus has positive charge and also alpha particle, which is basically helium nucleus. And it has a positive 2 charge. So both nucleus and alpha particle have the same charge. So what we will do? They will repel each other. And if they repel each other, it means they cannot attract. If we see here this line, this path, here particle is moving like this and then it is coming near to the nucleus. So if it is coming near, means there is attraction happening. And if there is attraction, that is not possible, as this will be the case of repulsion. So that's why we can say path C is not possible. So option C is the right answer. Moving ahead, an alpha nucleus of energy half mv square bombards a heavy nucleus target of charge Ze, then the distance of closest approach of the alpha nucleus will be proportional. So we know in this kind of situation, when we have a nucleus, suppose, and there is alpha particle coming towards it. So after some distance of approach, this alpha particle will stop and will revert back. Now at this distance, whole kinetic energy means initially this particle, alpha particle, had kinetic energy, and at this point the velocity becomes zero, so kinetic energy is zero, so means kinetic energy is converted into potential energy. So at this point the potential energy of the alpha particle will be equal to its initial kinetic energy, and that is basically energy conservation, and we can use this uh, we can say we can use this concept to find this distance r naught, because now this potential energy comes due to this nucleus, as alpha particle is in the interactive field of the nucleus, so that's why it has a certain potential energy. And here in the initial case it is very far away from the nucleus, so its potential energy is literally zero. So starting with that, we can write energy conservation that half mv square will be equal to the potential energy, that will be equal to 1 by 4 pi epsilon naught Ze into charge of alpha particle, that is basically, oh sorry, that is basically 2e, and divided by the distance, that is r. So from this, if we want to find expression for the distance, then r naught here, it will be equal to, this get cancelled, so that will be basically 1 by 2 pi epsilon naught into 1 by m into 2ze square divided by v square. So now in terms of velocity, r node is proportional to 1 by v square. In terms of mass, r node is proportional to 1 by m. In terms of charge, r node is proportional to ze square. So option A is rejected, B is possible, C is possible, D is rejected. So here we have two options which are possible. So any one of them can be a right answer. Moving ahead, an alpha particle of energy 5 MeV scattered through 180-degree angle by a fixed uranium nucleus, distance of closest approach. So we just calculated distance of closest approach in the previous one. Here, this is the distance of closest approach. So let me copy this expression and then we will substitute it. So paste, yeah. So we will use this formula to calculate distance of closest approach. So R node will be 1 by 2 pi epsilon naught. Now what I can do, I can write it 4 and 2 here. So 2 by 4 pi epsilon naught. So 2 will be as it is. And why I did this? Because I know the value of 1 by 4 pi epsilon. That is 9 to 10 raised to power 9. Into 1 by mass of the uranium nucleus. Now we can also do a further modification, because we don't want to get into the mass calculations and then we have to also calculate the velocity calculation. So what I can do, I can rewrite this whole expression like this: 4 by 2 pi epsilon naught into 2ze square divided by, this is m, this is v square, so I can write it like half mv square into 2. So this becomes the kinetic energy. And this 2 gets cancelled. So basically what I have, I can write it 1 by 4 by epsilon naught 2 square by kinetic energy. So this 2, let mark as 1. Now twice times Z. For the uranium nucleus, Z is 92. Yeah, Z is 92 into E square. So that will be 1.6 10 raised to power minus 19 square. And divided by kinetic energy. That is 5 MeV. So basically 5 mega electron volt. So 5 into 10 raised to power 6. And it is in electron volt. So we have to convert it into joule. So 1.6 10 raised to power minus 9. So this term will cancel this one. And what we will have? We will 9 into 2, that is 18 into 92 divided by 5. And in terms of 10 raised to power, we have 9 and minus 19. So this will give us minus 10. And this will go up. So minus 6. So 10 raised to power minus 16. Now I can approximate what I will do. Let us write 18 as 15 and 92 as 100. I'm approximating 15 into 100 divided by 5 into 10 raised to power minus 16. So this will be 3 or 300 into 10 raised to power minus 16. So this will be 3 into 10 raised to power minus 14, and this will be in meters. Now if I want in centimeters, so that will be 3 into 10 raised to power minus 12 centimeter. So what we have, that is closest to option A for me. So option A is the right answer. Now a particle of mass 200 MeV by c square collides with hydrogen atom at rest. Soon after the collision, the particle comes to rest and the atom recoils and goes to the first excited state. The initial kinetic energy of the particle is n by 4. Find the value of n. So in this question, what we have two type of concepts which we have to discuss. First one is collision, and then second one is excitation. Now, how this excitation will happen? We will need energy. And from where this energy will come? That will come from collision. And how we know that how this energy is going to come from the collision? That during this collision, there will be energy loss. And that energy loss will be absorbed by the atom, and that will lead to the excitation. So as there is energy loss, so this cannot be elastic collision. So it is basically non-elastic collision. Here it is mentioned that we are discussing collision of particles, and normally for particles collisions are elastic. But as there is excitation happening, so this will be a non-elastic collision. So in terms of non-elastic collision, what is conserved? Only momentum. Here momentum is conserved, not the energy. Only momentum is conserved. So let's start. So here we have a particle. First, this is our particle. It strikes with hydrogen atom, and that is hydrogen atom only. So not H2, H. And after what happens? That particles comes to rest. So initially its velocity is non-zero. Its velocity is 0. Now particle comes to rest. So velocity becomes 0. And this hydrogen atom recoils and goes into first excited. So this is excited now. So let's start with the momentum conservation. So for momentum conservation, we need mass and velocity. Mass of the particle is 200 MeV. 200 mega electron volt. Now coming to the hydrogen atom, we know this hydrogen atom has a proton plus electron inside it. Now mass of a proton is approximately 938 MeV, approximately. Now also let us remember mass of neutron, that is slightly higher, 939.6 MeV. And so hydrogen atom has a proton and electron, so its mass will be 938 plus 4 electron, it is 0.511 MeV. So that is basically 938.5 MeV. That is a total mass of hydrogen atom. Now what I will do here, I will use approximation. Why? Because if I take these values of masses, then it will become very difficult for me to do the exact calculation. So what I will assume that mass of hydrogen atom is 1000 MeV, so that they are in some proportion. So if mass of particle is n, then mass of hydrogen atom is basically 5. This is what approximation I'm taking, and I'm going ahead with this approximation. So if I conserve the momentum, and let's say final velocity of the particle hydrogen atom after collision is v2. So according to momentum conservation, what will I have? I have mv, that is the mass of particle with this velocity, so it's momentum, plus initial momentum of hydrogen atom, that is 0, and it will be equal to final momentum of the particle, that is 0, plus final momentum of the hydrogen atom, that is 5 mv2. So from this v2 comes out to be v by 5. And here keep in mind that this hydrogen atom is excited, but still it may be moving, and it has to move actually, because momentum has to be conserved. So it will be moving also, and it will be also absorbing some energy. So there will be some energy absorbed, and it will go to excitation, and there will be some energy which will go to kinetic energy for the hydrogen atom after collision. So now we have the expression for V2. Now what we can do, I can find out the change in kinetic energy. So delta KE. So here delta KE will be equal to change in kinetic energy. So that is total initial kinetic energy minus total final kinetic energy. Total initial kinetic energy will be half mv squared, and total final kinetic energy will be half 5m into v by 5 square. And if I solve this term, what I will get 2 by 5 mv squared. This is the change in kinetic energy, and this energy is used for excitation. So if this energy is used for excitation, now we know that for hydrogen atom there are fixed levels. If there are fixed levels, means their energy difference between the levels is also fixed. And assuming that transition is happening from the ground state, transition is happening from the ground state to the first excited state. So for the first excited state, we know that energy for the ground state for hydrogen atom is minus 13.6 electron volt, and energy for the first excited state, it is minus 3.4 electron volt. How we calculate? That is En is equal to minus 13.6 by n square electron. That how I can calculate excited state is for n is equal to 2. That is the first excited state. So here this delta E, the energy difference between both of these two, that will be 10.2 electron volt, and that should be equal to the excitation energy, and that should be equal to the 2 by 5 mv square. So from this I can write that 2 by 5 mv square is equal to 10.2 electron volt. Now what I have to calculate here, I have to find out initial kinetic energy. So initial kinetic energy will be half mv square. So let us multiply half here, and let us multiply half here also. So half mv square from this expression will be equal to this 2 by 5 will go here. So 5 by 2 into half into 10 by 2. So this will be 5 by 4 into 10.2. That is basically 12.75 electron volt. And we have to represent it as n by 4. So that can be written as 51 by 4. Yeah, 51, I think. Sorry, let us calculate actually. So it has to be written as n by 4, that is equal to 12.75. And from that, n will be equal to 48 plus 3, yeah, 51. So n will be equal to 51 here. So answer to this question that n is 51, and keep in mind that this is based on approximation that I assume that mass of hydrogen atom is approximately 1000 MeV, so that this calculation becomes slightly easier. Now let us move ahead. In the line spectra of hydrogen atom, difference between the largest and the shortest wavelength of Lehman series is 304 angstrom. The corresponding difference for the Paschen series will be. So we know that for hydrogen or hydrogen-like element, we have 1 by lambda is equal to r z square 1 by n1 square minus 1 by n2 square. This is the expression. Now difference between largest and shortest for the Lehman series. So let us do calculation for the Lehman series first. Lehman. So largest wavelength means lowest frequency or lowest energy. So for that, let's write as 1 by lambda lambda minimum. It will be equal to r times z is 1, and this is Lehman series. So n1 is 1 square minus 1 by infinite square. Why? Because we are calculating lambda minimum. So minimum wavelength means maximum frequency means maximum energy. So maximum difference between the levels. So from this, lambda minimum is that is basically r, yeah, 1 by r. Now for maximum, 1 by lambda maximum. So lambda maximum means minimum energy difference, means both of the levels are nearby. So that will be r 1 by 1 square minus 1 by 2 square. And from this, lambda max will be equal to 4 by 3r. Now let's do same for the okay, their difference is given to us. The difference is given to us, so means 1 by r minus 4 by 3r. Oh, sorry. Lambda max minus lambda minimum will be there. So 4 by 3r minus 1 by r is equal to 304 angstrom. And that can be written as like 3 by 3r. So basically 4 minus 3, that is 1. So 1 by 3r is equal to 304 angstrom. So from this, 1 by r is equal to 912 angstrom. Okay, so let's move for the Paschen series. So we know Lehman, Balmer, Paschen, bracket, and P fund. So for Paschen, our N1 is equal to 3. And we have to find out the same difference that for the minimum and maximum. So for the Paschen series, 1 by lambda minimum will be equal to R 1 by 3 square minus 1 by infinite square. So from that, lambda minimum comes out to be 9 by R. And going to the lambda maximum, 1 by lambda maximum, that will be equal to r 1 by 3 square minus 1 by 4 square, and from that lambda max will be 16 minus 9, that will be 7 by 144. Oh, sorry. Yeah, 144 by 7r. Now we can calculate the difference. So their difference will be 144 by 7r minus 9 by r, and that will give us 81 by 7r, and that will be 81 by 7 into 912, and that will be further 10553.1 angstrom. Now let's match it. Okay, so we have to fill it. So answer will be 10553.1 angstrom. So that will be the answer here. Now moving ahead to the next one. In the hydrogen atom, electron makes a transition from n plus 1th level to nth level if n is very large, n is greater than 1, frequency of the radiation emitted. So for that, what we can do? We know that energy of the nth level will be equal to minus 13.6 by n square, and energy of the n plus 1th level will be minus 13.6 by n plus 1 square. So the energy difference between these two levels for which there will be a radiation emission, so that will be equal to delta E. It will be minus 13.6 by n square minus minus plus 13.6 by n plus 1 square. So that can be written as like this, that if we take 13.6 common, and that will be 1 by n plus 1 square minus 1 by n square. Now this can be expanded further, 13.6 n square into n plus 1 square. Here we'll get n square minus n plus 1 square, that will be n square minus 1 minus 2n. Okay, I think I had to add a negative sign here. So only then this will be positive. So put negative sign. So this n square is cancelled, and I am left with minus 1 minus 2n adjusting with the negative sign. So that will be 13.6 into 1 plus 2n divided by n square into n plus 1 square. Now here it is mentioned that n is greater than 1. So what we can do? We can find use binomial approximation. So how we will do it? I will take n common from the upper side. So that will be n into 1 plus, 1 by n plus 2 and divided by n square, and from this term also I will take n common, so it will come outside as n square 1 plus 1 by n whole square. Now we know that n is very large, so 1 by n will be approximately equal to 0. That is the limiting case, and this n cancels this one. So what I will have 13.6 into 2. 1 by n is basically 0 divided by n into n square, that is n cube, and this term is basically 1 square, so 1 square is 1. So here I have n cube. So the energy gap is proportional to 1 by n cube, and we know that delta E will be equal to h times the frequency. So frequency will also be proportional to 1 by n cube, and that is option B for us. So with this, we end this video here. Hopefully whatever we have covered is helpful to you. Again, if you have any doubts or suggestions, you can put them in comment section. I would like to help. And like this video, then share them, subscribe to our channel, and If you like to support us, then scan the QR codes and donate whatever amount you want. Any amount of help will be highly appreciated. With this, again, thanks for watching, and we will meet in next video.